Just over 4 light-years from Earth lies a star so similar to our own Sun that astronomers once assumed it would be an easy place to search for planets. For decades, they tried and failed. The star's brilliance overwhelmed instruments. Its stellar companion interfered with observations. Its rapid motion across the sky complicated long exposures. Every method came up empty. Then, something unexpected happened. The James Webb Space Telescope turned its gold-plated eye toward Alpha Centauri, and for a brief moment, something appeared. A dim point of light flickered beside the star, then vanished. Subsequent observations found nothing at all. If a planet was there, it had slipped away. What JWST glimpsed in our nearest stellar neighborhood challenged nearly every assumption we've made about discovering worlds beyond our solar system. If you want to follow what could become the most important exoplanet detection ever attempted, now's the time to stay with us. Let's start at the beginning. Alpha Centauri is not just another star among countless pinpricks in the night sky. It is our closest stellar neighbor, the nearest possible destination for any future interstellar mission, the cosmic doorstep of our solar system. For more than 7 decades, astronomers have been haunted by a deceptively simple question: does it host planets? Again and again, the answer remained frustratingly out of reach. This failure had nothing to do with a lack of expertise or tools. Humanity has already confirmed nearly 6,000 exoplanets using a wide range of techniques refined over generations. Some planets reveal themselves by the subtle gravitational tug they exert on their stars. Others betray their presence by briefly dimming starlight as they pass in front of their host. Still others are captured directly as faint glowing embers orbiting faraway suns. The science works, the methods are proven, but Alpha Centauri refused to cooperate. The system violates nearly every rule astronomers rely on when searching for planets. Ironically, what should make it the easiest target in the sky turns it into one of the most difficult objects ever studied. Alpha Centauri sits a mere 437 light-years from Earth. On cosmic scales, that distance is almost negligible. Light leaving the system tonight reaches Earth in less than 4.5 years. A photon emitted when you began high school would arrive before you graduate college. Compared to the hundreds or thousands of light years separating us from most known exoplanet systems, Alpha Centauri is practically next door. This proximity should be a massive advantage. Objects closer to us appear brighter and larger. A planet invisible at 100 light years should stand out clearly at 4. In theory, Alpha Centauri should be the ultimate exoplanet laboratory. In practice, its closeness creates new obstacles instead of solutions. The system is blindingly bright. Its light overwhelms the ultra-sensitive detectors designed to isolate faint planetary signals. Trying to spot a planet there is like attempting to photograph a candle flame beside a stadium floodlight. Alpha Centauri A, the primary star, is the 3rd brightest star visible from Earth. Only Sirius and Canopus shine more intensely. From the southern hemisphere, it dominates the constellation Centaurus, glowing with a yellow-white brilliance that ancient navigators once used to cross uncharted oceans. Its companion star, Alpha Centauri B, makes matters worse. The 2 sun-like stars orbit each other every 80 years, swinging as close as 11 astronomical units and drifting as far apart as 36. During observations, light from the companion spills into detectors, contaminating measurements and drowning out anything faint enough to be a planet. A 3rd star, Proxima Centauri, lurks far beyond the central pair, about 13,000 astronomical units away. This dim red dwarf emits less than 1% of the Sun's luminosity and takes more than 500,000 years to complete a single orbit around the system's center of mass. Astronomers have already confirmed at least 2 planets around Proxima, with a 3rd still under investigation. But these worlds orbit a star so different from our Sun that comparisons to Earth are deeply limited. Red dwarf planets endure violent stellar flares capable of stripping atmospheres. Many become tidally locked, with one side baked in eternal daylight and the other frozen in endless night. Their habitable zones sit dangerously close to their stars, creating extreme gravitational and radiation environments. Planets around Alpha Centauri A or B would be a different story entirely. These stars closely resemble our Sun in mass, size, temperature, and age. Any planets orbiting them would experience conditions far more comparable to Earth's. Detecting such worlds would be revolutionary, but separating their faint light from overwhelming stellar glare is extraordinarily difficult. The brightness difference between a Sun-like star and a Saturn-sized planet exceeds 10,000 to 1. Detecting that signal means isolating something 10,000 times fainter than the background light flooding the telescope. The James Webb Space Telescope was never intended for this task. JWST was designed to study the earliest galaxies in the universe. Objects so distant, their light has traveled billions of years before reaching us. Its detectors were optimized to capture the faintest whispers of ancient photons, not to stare down one of the brightest stars in our sky. Pointing Webb at Alpha Centauri seemed almost reckless, like using a scalpel to cut down a tree or piloting a submarine up a mountain. With a price tag nearing $10 billion and more than 2 decades of development behind it, JWST was considered too valuable to risk. Many astronomers argued that bright targets should be avoided entirely to protect its delicate instruments. But one scientist refused to let that caution end the story. Charles Bateman of NASA's Jet Propulsion Laboratory and the NASA Exoplanet Science Institute had been dreaming of planets around Alpha Centauri long before Webb ever launched. He assembled a team willing to challenge conventional wisdom. Their idea focused on Webb's mid-infrared instrument, MIRI, and a different strategy altogether. Searching for heat instead of reflected starlight. Planets absorb energy from their stars and re-emit it as infrared radiation. A world in the habitable zone of Alpha Centauri A would likely maintain temperatures between 200 and 350 Kelvin, cool enough to glow faintly in mid-infrared wavelengths, exactly where MIRI is most sensitive. This approach is especially effective for older planetary systems. Young planets still radiate leftover heat from their formation and shine brightly in near-infrared light. But mature planets, billions of years old, have long since cooled. Their thermal emissions peak at longer wavelengths that only specialized instruments can detect. Alpha Centauri A is roughly 5 billion years old, nearly the same age as our Sun. Any planets there would be ancient, cold worlds, glowing only through the warmth they absorb and re-radiate from their star. MIRI's 15.5 micron filter offered the best chance of detecting that faint heat, but only if the star's glare could be suppressed. That's where the coronagraph comes in. MIRI includes a device designed to block starlight using a physical mask called a 4-quadrant phase mask. Placed precisely over the star's image, it creates an artificial eclipse, dramatically reducing stellar brightness while allowing nearby objects to remain visible. The technique relies on destructive interference. Light waves cancel each other out, reducing the star's glare by orders of magnitude. Meanwhile, light from off-center sources, like orbiting planets, passes through with far less interference. In principle, this level of contrast turns the unthinkable into something barely achievable. And, with the extraordinary sensitivity of Webb, the risk finally made sense. Under normal circumstances, JWST's coronagraph performs exceptionally well. Most stars targeted in exoplanet searches sit at comfortable distances and exhibit brightness levels well within the telescope's operational limits. Standard acquisition routines lock onto these stars smoothly, and observations follow procedures refined through hundreds of successful programs. Alpha Centauri, however, violated every assumption behind those routines. The first and most fundamental problem is motion. Alpha Centauri exhibits one of the fastest proper motions of any star visible to the naked eye. It slides across the sky at roughly 3.7 arcseconds per year, a shift large enough to be noticeable over a human lifetime. While that number sounds insignificant, it becomes critical when dealing with the extreme precision required for coronagraphic imaging. JWST must keep the star positioned perfectly behind the coronagraphic mask. Deviations as small as 10 milliarc seconds allow stellar light to leak around the mask, destroying the contrast. Tracking Alpha Centauri demanded pointing accuracy beyond anything previously attempted with the telescope. The second complication comes from the system's binary nature. Alpha Centauri B currently orbits close enough that its intense light spills into the MIRI detector, scattering across the entire field. No coronagraph can block 2 bright stars simultaneously when they occupy different positions. Even if Alpha Centauri A were perfectly suppressed, the companion's glare would still contaminate the image, overwhelming any faint planetary signal. The third obstacle is sheer brightness. Alpha Centauri A exceeds the brightness limits assumed for standard JWST operations. Acquisition procedures that work flawlessly for ordinary stars would saturate the detectors when aimed at this stellar powerhouse. The telescope's guidance systems were never designed to lock onto an object this luminous. Those limits exist for a reason: to prevent irreversible damage to the instruments. The fourth challenge lies in the background itself. Alpha Centauri sits directly along the plane of the Milky Way, where countless faint background stars crowd every image. Any detected point of light must be carefully distinguished from unrelated sources. A dim signal could represent a planet orbiting Alpha Centauri, or it could be a distant galaxy billions of light years away that just happens to align with the system. Faced with these issues, the operations team at the Space Telescope Science Institute confronted a near-impossible task. They had to invent observing strategies never before used with JWST. Established procedures were useless. Every element of the observation demanded innovation, precision, and a willingness to push the telescope beyond its original design envelope. The breakthrough came after months of simulations and planning. The team devised a strategy known as blind offsetting, designed to avoid direct acquisition of the blinding target. Instead of pointing at Alpha Centauri A, JWST would first lock onto a nearby reference star with manageable brightness. The chosen star was Epsilon Muscae, a red giant roughly 330 light-years away in the constellation Musca. Its luminosity falls comfortably within standard acquisition limits, allowing the telescope's guidance systems to operate normally. Once locked onto Epsilon Muscae, the telescope would execute a precisely calculated offset maneuver, placing Alpha Centauri A behind the coronagraphic mask without ever pointing directly at it. This maneuver required extraordinary positional accuracy. Even a tiny error would misalign the star relative to the mask, flooding the detector with light and invalidating the observation. The calculations had to account for Alpha Centauri's rapid proper motion and its significant parallax. At just 1.34 parsecs from Earth, the system's apparent position shifts by about 750 milliarc seconds as Earth moves around the Sun. This seasonal parallax means the star's coordinates change continuously. Values that worked in January would be wrong by March. The team developed custom software pipelines that recalculated offset positions dynamically based on the exact timing of each observation. Nothing about Alpha Centauri could be treated as fixed. The first attempts, conducted in 2023, were total failures. Technical complications rendered the data unusable. The telescope struggled to maintain precise positioning while compensating for motion and extreme brightness. Coronagraphic performance fell short of what was required, and scattered light from Alpha Centauri B dominated the images. For many teams, this would have been the end. The outcome seemed to confirm the skeptics. Alpha Centauri was simply beyond JWST's practical reach. But Bachmann's team refused to quit. They dissected every failure, identified each weakness, and rebuilt the strategy from the ground up. Pointing routines were refined to improve centering accuracy. New data processing techniques were developed specifically to mitigate contamination from the companion star. Every adjustment was tested through exhaustive simulations before another observation was attempted. By mid-2024, the revised approach was ready. Test observations showed dramatic improvement. JWST could now observe Alpha Centauri with sensitivity approaching theoretical limits. The team received approval for a full observing campaign. In August 2024, Webb executed 3 extended observation sequences focused on Alpha Centauri A. Each exposure lasted several hours, with the coronagraph suppressing stellar light, while the detectors collected whatever faint signals emerged from the surrounding space. As data streamed back from the telescope's position at Lagrange point 2, anticipation mixed with anxiety. The raw images looked exactly as expected. Utter chaos. Light contamination, diffraction patterns, and detector artifacts filled the frames. Alpha Centauri B blazed near the edge of each image, its scattered light producing streaks and halos across the field. The coronagraph introduced complex ripple patterns as residual starlight diffracted around the mask. To the naked eye, the images appeared meaningless. Abstract noise with no discernible structure. Extracting real science required advanced processing techniques developed for extreme high-contrast imaging. The team applied reference star differential imaging, observing other stars under identical coronagraphic conditions to create templates of the instrument's behavior when no planet is present. Subtracting these templates removed systematic optical artifacts while preserving signals unique to Alpha Centauri. Additional algorithms, including principal component analysis and Karhunen-Loew image processing, removed remaining correlated noise. These mathematical tools isolate and strip away residual contamination that simpler methods cannot eliminate. Step by step, layer by layer, the hidden structure began to emerge. What finally appeared stunned everyone involved. At a distance of roughly 1.5 arcseconds from Alpha Centauri A dim source emerged in the fully processed images. The research team designated it S1. Its brightness was astonishingly low, more than 10,000 times weaker than the glare of its host star. Based on its angular separation, the object appeared to lie at a projected distance of approximately 2 astronomical units from Alpha Centauri A. From a statistical standpoint, the detection reached a confidence level of 5.5 sigma. Against every expectation, something tangible had surfaced. That statistical threshold matters. It measures the likelihood that the observed signal could be produced by random noise rather than a real astronomical object. At 5.5 sigma, the odds drop to less than 1 chance in 10 million. Random fluctuations almost never create signals of this strength. Whatever S1 was, it was not a coincidence. Immediate scrutiny followed. Before even hinting at a planetary discovery, the team had to eliminate every alternative explanation. A planet orbiting Alpha Centauri would represent one of the most consequential findings in exoplanet science. Such a claim demanded evidence capable of surviving the harshest skepticism. One possibility was that S1 was not local at all, but a distant background galaxy masquerading as a point source. Compact galaxies can appear unresolved, even through powerful space telescopes. To test this, the team cross-checked the detection against all available astronomical catalogues of known background objects. No match appeared. Nothing previously identified occupied that location. Another concern was the possibility of a foreground object, perhaps an asteroid drifting through the line of sight during the long exposure. Solar system bodies occasionally pass unnoticed through deep observations. Motion analysis quickly ruled this out. The signal remained fixed relative to Alpha Centauri A throughout the observation window. A nearby moving object would have shifted position measurably. Instrumental effects posed an even subtler threat. Complex optical systems can generate spurious signals unrelated to any real object in space. To address this, the team conducted extensive injection and recovery tests. Artificial planetary signals were inserted into raw data to determine whether genuine detections could be reliably distinguished from processing artifacts. Real sources leave consistent, measurable fingerprints that false positives do not. S1 passed every test designed to expose an illusion. The August 2024 data strongly suggested the presence of a planet candidate orbiting the closest Sun-like star to Earth. If verified, the discovery would rank among the most important milestones in planetary science. After decades of searching, humanity might finally have evidence of a world circling its nearest stellar twin. Yet the team understood the limits of a single observation. True planets do not remain fixed. They follow predictable paths dictated by gravity. Their positions shift over time in accordance with Kepler's laws. To confirm S1 as a genuine planet, rather than an exotic anomaly, astronomers needed to observe it again and watch it move. Recognizing the urgency, the Space Telescope Science Institute granted directors discretionary time for rapid follow-up. This rare allocation exists precisely for moments like this, when scientifically critical targets cannot wait for standard proposal cycles. The Alpha Centauri candidate easily met that standard. 2 additional observation campaigns were scheduled for early 2025. February and April would replicate the August setup as closely as possible. If S1 were real, it should reappear at different locations, tracing an orbital arc around Alpha Centauri A. The direction and magnitude of that motion would constrain its orbital period and geometry. As the dates approached, anticipation spread through the astronomical community. Whispers circulated at conferences and across online forums. The closest Sun-like star to Earth might finally have a directly imaged planet. A system contemplated for centuries by philosophers and scientists alike could at last reveal its planetary companion. The implications extended far beyond a single detection. Alpha Centauri A is remarkably similar to our Sun. Its mass exceeds solar mass by only about 10%. Its radius is nearly identical. Its surface temperature, around 5,790 Kelvin, differs by less than 200 degrees from the Sun's photosphere. Its luminosity is roughly 50% greater. A planet orbiting such a star would offer an unprecedented laboratory for comparison with our own solar system. Until now, every directly imaged exoplanet has orbited young, massive stars fundamentally unlike the Sun. Those systems reveal how planets behave during early, chaotic stages of evolution. They tell us little about mature planetary environments like our own. A planet around Alpha Centauri A would be the first directly imaged world bathed in truly sun-like radiation. Scientists could, for the first time, study how planetary atmospheres respond to a solar-type spectrum. They could search for chemical signatures associated with geology, or even biology. Preliminary analysis of the August data suggested S1 had an effective temperature near 225 Kelvin, about -48 degrees Celsius. That temperature placed it near the outer edge of Alpha Centauri A's habitable zone, the region where liquid water could theoretically exist on rocky surfaces. S1 itself, however, appeared to be a gas giant. Estimates based on its brightness and temperature pointed to a mass between 90 and 150 Earth masses, comparable to Saturn's 95 Earth masses. Gas giants cannot host liquid oceans or Earth-like life. Their deep atmospheres and lack of solid surfaces rule out familiar biological processes. But gas giants often come with moons. Saturn alone has more than 270 known satellites, ranging from small captured objects to large complex worlds. Titan possesses a dense nitrogen atmosphere thicker than Earth's. Enceladus hides a global ocean beneath its icy shell. Either could potentially support microbial life. A Saturn-mass planet within the habitable zone of our nearest Sun-like star could host moons where liquid water and biochemistry exist. That possibility transformed theoretical curiosity into urgent scientific priority. The detection also challenged long-standing models of planet formation in binary star systems. Alpha Centauri A and B orbit each other at distances thought to disrupt planetary growth. Simulations consistently predicted that protoplanetary material would be stripped away before planets could form. Stable orbits were expected only very close to each star or far from the binary pair altogether. Yet, S1 appeared to reside in a marginally stable region, exactly where theory suggested planets should struggle to survive. If confirmed, the discovery would force theorists to rethink how planets form and persist amid the gravitational complexity of binary systems. Perhaps planets are more resilient than models assume. Perhaps formation pathways exist that current simulations fail to capture. Confirmation, however, required motion. The February and April 2025 observations were expected to deliver decisive evidence. Orbital movement would distinguish a real planet from background contamination or instrumental artifacts. What no one anticipated was how strange the outcome would be. The February 2025 observations unfolded flawlessly. Every subsystem aboard the James Webb Space Telescope performed exactly as intended. The blind offset maneuver positioned Alpha Centauri A perfectly behind the coronagraph. The telescope held its aim with extraordinary stability, while detectors gathered photons for hours. The data arrived from Lagrange Point 2 almost instantly, crossing the million-mile void in seconds. Researchers gathered at their monitors, prepared to process images that could confirm the most consequential planetary discovery in decades. What emerged instead only compounded the mystery. For months, the August detection had kept astronomers on edge. Now, verification seemed imminent. As soon as the new data landed, the analysis pipeline sprang into action. Massive volumes of raw detector output flowed into processing systems honed through years of prior observations. Reference star subtraction removed systematic coronagraphic artifacts that would otherwise overwhelm the field. Principal component analysis isolated and stripped away correlated noise buried beneath the dominant signals. The same methods that had revealed S1 in August were now applied with exacting consistency to the February dataset. Layer by layer, contamination peeled away. The algorithm searched precisely where orbital models predicted S1 should reappear. But nothing surfaced. The location that had produced a 5.5 sigma signal just months earlier, showed only empty space. No strong detection rose above the noise. No faint hint suggested the presence of a planet. The field contained nothing beyond random fluctuations. The team immediately questioned the result. A processing failure? An inappropriate parameter choice? They reran the entire pipeline with adjusted settings, tested alternative algorithms, and scrutinized the raw frames directly in case genuine signals had been inadvertently removed. Every attempt led to the same conclusion. The February observations showed no detectable planet anywhere within the coronagraph's sensitive region around Alpha Centauri A. S1 was gone. April 2025 offered one final opportunity. Perhaps February had coincided with unfavorable conditions. Perhaps orbital motion had briefly placed the object in a region of poor sensitivity, only to return it to view weeks later. 2 additional months of movement might make all the difference. When the April data arrived, it underwent identical analysis. Once again, the pipeline searched relentlessly for any trace of the August signal. Scientists combed through every corner of the field with near desperate precision. The result was unmistakable. More empty space, more null detections. Whatever JWST had captured in August 2024 no longer revealed itself, even to the most powerful space telescope ever built. Aniket Sethi, a doctoral researcher at the California Institute of Technology and co-first author of the discovery papers, summarized the situation with unsettling clarity. The team was facing a disappearing planet. An object that had ignited excitement across the astronomical community appeared to have dissolved into nothingness between observation epochs. Such an outcome demanded explanation. Planets do not simply vanish. Objects bound by gravity follow deterministic paths dictated by celestial mechanics. If S1 were truly orbiting Alpha Centauri A, it should have appeared somewhere in every subsequent observation, even if its position changed. 3 possible explanations remained. Each carried serious implications for what JWST had actually detected in August. Each required careful evaluation against the full body of evidence. The first possibility was the least satisfying. Perhaps S1 had never been real. Despite surviving every statistical test and artifact rejection procedure, the August signal could represent an extraordinarily rare fluctuation in detector noise that coincidentally mimicked a genuine astronomical source. Random processes occasionally produce patterns that appear meaningful. Flip a coin often enough, and improbable sequences inevitably occur. Electronic detectors operating near their sensitivity limits experience quantum fluctuations capable of generating spurious readings. This explanation was difficult to accept. A 5.5 sigma detection corresponds to odds of less than 1 in 10 million that noise alone could produce such a signal. Detection thresholds are deliberately set to exclude events this unlikely. Accepting this scenario meant accepting extreme bad luck. Moreover, the team had split the August dataset into independent segments and analyzed them separately. Each subset reproduced the S1 signal at the same position with consistent brightness. Noise rarely behaves so coherently across independent data. Still, statistics can never fully rule out false positives. Given enough observations, even 1 in 10 million events will eventually occur somewhere in the universe. The second possibility involved background contamination. Astronomical images capture everything along the line of sight, including distant galaxies billions of light years away. Some compact galaxies appear point-like, even to powerful telescopes, and can masquerade as nearby planets. Perhaps an uncatalogued background source coincidentally aligned with Alpha Centauri A during the August observation. If that object possessed its own motion, it might have shifted out of view by February. The team investigated this explanation exhaustively. They consulted data from the Gaia spacecraft, which has precisely mapped the positions and motions of nearly 2 billion stars in the Milky Way. No stellar source appeared anywhere near the S1 location at any Gaia epoch. They searched archival images from ground-based and space-based observatories spanning decades. Deep exposures at multiple wavelengths revealed no background object consistent with the detected signal. The region around Alpha Centauri A appeared genuinely empty. They also examined the spectral properties of the detected light. Distant galaxies typically exhibit color signatures distinct from those of cool, thermally emitting planets. S1's emission profile matched expectations for a cold planetary object rather than a background galaxy. Every test designed to expose contamination returned negative results. The third explanation was the most intriguing. S1 might be a real planet that simply moved beyond the coronagraph's detection capabilities between observation epochs. Understanding this possibility requires appreciating how coronagraph sensitivity varies across the field of view. Coronagraphs do not provide uniform sensitivity at all angles around a star. Physics dictates that some regions are exquisitely sensitive, while others are effectively blind. The coronagraph blocks the central stellar image with a mask, creating an artificial eclipse that suppresses overwhelming starlight. But no physical structure can block electromagnetic radiation perfectly. Light waves bend around edges through diffraction. When starlight encounters the boundaries of the coronagraphic mask, some of it bends rather than being blocked outright. This diffracted light produces complex residual patterns extending outward from the star. Close to the star, these diffraction effects overwhelm any planetary signal. Farther out, detector noise dominates. Only within a narrow range of angular separations does sensitivity peak high enough to detect the extreme contrast ratios required for planet imaging. If S1's orbit carried it into one of the coronagraph's blind zones sometime between August and February, the planet would not have vanished in any physical sense. It would have become invisible, not because it ceased to exist, but because the laws of optics temporarily erased it from view. And that realization changes the entire interpretation. There exists a narrow region around a star where coronagraphic detection becomes possible, a kind of observational sweet spot. That region is far smaller than many astronomers initially assumed. Even more critically, sensitivity is not uniform around the star. It varies sharply with position angle. The four-quadrant phase mask used by MIRI suppresses starlight unevenly, depending on how its geometry interacts with the telescope's mirrors, support structures, and diffraction patterns. Along some directions, stellar suppression is superb. Along others, residual glare overwhelms everything. A planet can therefore be detectable in one direction from its star and completely invisible in another, even at the same orbital distance. As orbital motion carries the planet around the star, it can rotate into a region where the coronagraph performs poorly and simply disappear from view for months at a time. Orbital shape complicates matters further. If S1 follows an elliptical orbit rather than a near-circular one, its distance from Alpha Centauri A changes continuously throughout its year. At certain phases, the planet moves closer to the star, where diffraction dominates and coronagraphic sensitivity collapses. At other phases, simple geometry may place the planet directly in front of or behind the star from Earth's perspective, hiding it completely. In either case, a real planet could evade detection without violating any physical principle. The February and April non-detections, therefore, do not automatically imply that S1 never existed. They may simply indicate that the planet occupied an unfavorable orbital position during those epochs, one beyond the reach of current technology. To test this idea, the team turned to extensive orbital simulations. They explored every plausible trajectory consistent with the available data, generating millions of hypothetical orbits with different periods, eccentricities, inclinations, and orientations. Each candidate orbit also had to remain gravitationally stable in the presence of Alpha Centauri B, whose influence cannot be ignored. These simulations incorporated a crucial clue that had nearly been forgotten amid the excitement surrounding JWST. In 2019, astronomers using the European Southern Observatory's Very Large Telescope in Chile detected a faint signal near Alpha Centauri A. This ground-based candidate, labeled C1, appeared at a separation of roughly 1.1 astronomical units. The observation came from a mid-infrared instrument specifically designed for high-contrast imaging of nearby stars. However, ground-based observations suffer from severe limitations. Earth's atmosphere constantly distorts incoming light through turbulence and temperature gradients. Adaptive optics can correct some of this distortion, but never completely. Residual atmospheric effects generate false structures that can masquerade as planets. As a result, the C1 signal never achieved confirmation status. Most astronomers treated it as an intriguing hint rather than a discovery. But what if C1 and S1 were the same object? A planet on an eccentric orbit would appear at different separations depending on when it is observed. The 2019 ground-based hint and the 2024 space-based detection could represent brief glimpses of a single planet moving along an elongated path. If so, combining both detections would dramatically restrict the range of allowed orbits. Any viable orbit would need to place the planet near 1 astronomical units in 2019, near 2 astronomical units in August 2024, and somewhere undetectable during February and April 2025. The team investigated whether such an orbit could exist while remaining physically realistic and gravitationally stable. The computational effort was enormous. Millions of orbital configurations were tested against detection and non-detection epochs, all while enforcing stability constraints within the Alpha Centauri binary system. The outcome surprised everyone. The simulations showed that approximately 52% of all gravitationally stable orbits consistent with both S1 and C1 would naturally produce non-detections in February and April 2025. In these scenarios, the planet moves into regions where JWST's coronagraph simply lacks the sensitivity to see it during those months. This result fundamentally reframed the mystery. Rather than contradicting the planetary hypothesis, the non-detections were entirely consistent with it. The planet had not behaved anomalously. It had behaved exactly as orbital mechanics predicted for more than half of all allowed configurations. In other words, invisibility was not a problem. It was expected. The surviving orbital solutions depict an unusual and scientifically rich system. S1 appears to follow a strongly eccentric orbit, with its distance from Alpha Centauri A varying dramatically over each cycle. Current models suggest an eccentricity near 0. 4, meaning the planet's closest approach is only about 60% of its maximum distance. For comparison, Earth's orbit is almost perfectly circular, with an eccentricity below 2%. Mars reaches about 9%. Mercury, the most eccentric major planet in our solar system, peaks at roughly 21%. An eccentricity near 40% places S1 well outside the range of anything in our planetary neighborhood, rivaled only by certain dwarf planets and long-period comets. The planet's orbital period appears to fall between 2 and 3 Earth years. At perihelion, it approaches Alpha Centauri A to roughly 1 astronomical unit, similar to Earth's distance from the Sun. At aphelion, it retreats to nearly 2 astronomical units, comparable to Mars's orbit. This wide swing naturally explains why the planet appears at some times and vanishes at others. During perihelion, S1 hides deep within the stellar glare, where coronagraphic suppression fails. Near aphelion, it emerges into regions where Miri achieves sufficient contrast. The August 2024 observation likely caught the planet near aphelion. By February and April 2025, it had moved inward, beyond JWST's reach. The planet did not disappear. It slipped behind the limits of our instruments. Perhaps the most unexpected aspect of the reconstructed orbit involves its inclination. Alpha Centauri A and B orbit each other in a plane inclined about 79 degrees relative to our line of sight. Planets forming from the same protoplanetary disk would normally share that orientation. S1 does not. Instead, the planet appears to orbit at roughly 50 degrees relative to the binary plane, a dramatic misalignment. Such a tilt challenges standard formation models, which predict that planets inherit the angular momentum of their natal disks. This misalignment implies either exotic formation conditions or significant post-formation evolution. One possibility is past gravitational encounters with other planets that were later ejected from the system, leaving S1 on a tilted orbit. Another involves long-term gravitational interactions between the planet, its host star, and the binary companion, slowly altering the orbit through resonant effects. A tilted orbit also raises questions about long-term stability. Planets inclined relative to binary planes can experience gravitational torques that drive oscillations in eccentricity and inclination over millions of years. In extreme cases, these interactions can destabilize orbits entirely. Detailed stability analyses, however, indicate that S1 remains securely bound for billions of years. Despite its unusual geometry, the planet never approaches Alpha Centauri B closely enough for the companion's gravity to destabilize it. Even at maximum separation, S1 stays well within Alpha Centauri A's gravitational domain. Meanwhile, Alpha Centauri b currently orbits at a distance of roughly 20 astronomical units, far enough to avoid catastrophic disruption. What emerges is not a tidy, orderly planetary system, but a dynamically intricate one, far more complex and far more revealing than anyone initially anticipated. Even when the binary stars reach their closest approach of roughly 11 astronomical units, the secondary remains too distant to exert strong gravitational disruption on a planet orbiting within 2 astronomical units of the primary. In that region, Alpha Centauri A overwhelmingly dominates the gravitational environment. The companion star contributes only weak perturbations, leaving a stable zone where long-lived planetary orbits can persist. That said, orbital constraints derived from only 4 observation epochs come with substantial uncertainty. 2 positive detections, one from 2019 and another from August 2024, combined with 2 non-detections in early 2025, simply do not provide enough information to pin down a single, precise orbit. A wide range of configurations remain mathematically consistent with the available data. Orbital eccentricity could plausibly fall anywhere between 0.2 and 0.6. Periods ranging from roughly 18 months to nearly 4 years satisfy the timing of both detections and absences. Inclination angles between 30 and 70 degrees also remain viable. Each new observation will gradually shrink these ranges, pruning away incompatible solutions and sharpening the picture. The team documented their findings in 2 peer-reviewed papers, accepted for publication in the Astrophysical Journal Letters, one of the most respected journals in astronomy. The first paper focused on the observations themselves, detailing the detection, photometric measurements, statistical significance, and orbital modeling. The second paper addressed the image processing techniques, sensitivity limits, and systematic error analysis required to extract a marginal signal from extraordinarily difficult data. Both studies were careful to emphasize an essential point. S1 remains a planet candidate, not a confirmed planet. No matter how strong the statistics appear, a single robust detection cannot prove planetary nature on its own. True confirmation requires tracking the object across multiple orbital phases and demonstrating motion consistent with a gravitationally bound orbit around the host star. The authors also explored alternative explanations that could, in principle, account for the August signal without invoking a planet. One such possibility involves dust. Circumstellar debris, created by asteroid collisions or cometary activity, can sometimes appear as compact, point-like sources in high-contrast coronagraphic images before dispersing or drifting out of view. The observed brightness and color of S1 are consistent with either a planetary atmosphere or a dense dust cloud heated by stellar radiation. Both would emit thermal infrared radiation at similar temperatures given their distance from Alpha Centauri A. Discriminating between these scenarios requires future observations at multiple wavelengths capable of probing compositional differences. Another possibility is that S1 could be a brown dwarf rather than a planet. Brown dwarfs occupy the mass range between giant planets and true stars. They generate internal heat through gravitational contraction and brief deuterium fusion, but never sustain hydrogen burning. In thermal emission, they can resemble massive planets. However, estimates based on S1's brightness and temperature place it well below the brown dwarf threshold. Brown dwarfs typically exceed 13 Jupiter masses, roughly 4,000 Earth masses. S1 appears far lighter than that, though uncertainties in mass estimates remain significant. The team also considered whether the signal might arise from multiple smaller objects rather than a single large one. Swarms of asteroids or cometary debris could, under rare circumstances, produce a combined signal resembling a planet. Statistical analysis and the point-like nature of the detection made this explanation less likely than the single planet hypothesis, though it could not be ruled out entirely. The broader scientific community responded with a blend of cautious skepticism and genuine excitement. Extraordinary claims demand extraordinary evidence, and the idea of a directly imaged planet around our nearest sun-like neighbor certainly qualifies. The case for S1 currently rests on one strong detection, supported by orbital modeling that explains subsequent non-detections. That alone is not enough for confirmation, but if confirmation ultimately arrives, S1 would claim several historic distinctions. It would become the closest known exoplanet orbiting within the temperate zone of a Sun-like star. Although planets around Proxima Centauri are slightly closer in absolute distance, they orbit a red dwarf, a fundamentally different stellar environment. Habitable zones around red dwarfs differ dramatically from those around Sun-like stars in radiation, stability, and long-term habitability. S1 would also be the nearest directly imaged exoplanet by a wide margin. Every other planet captured through direct imaging orbits stars at least 10 times farther away. That proximity unlocks observational possibilities unavailable for distant systems. It would be the oldest directly imaged exoplanet ever detected. Previous successes in direct imaging have focused almost exclusively on very young systems, less than 100 million years old, where planets still glow from formation heat. Alpha Centauri A is billions of years old, offering a mature planetary environment comparable to our own solar system. S1 would also be the coldest directly imaged exoplanet. The current sample is dominated by hot, luminous worlds. Detecting a cold, mature planet would open a new observational regime long considered inaccessible. Finally, it would orbit closer to its host star than any directly imaged planet known. Most imaged planets lie tens or hundreds of astronomical units from their stars, far beyond habitable zones. S1 appears to orbit within 2 astronomical units, comparable to Mars's position in our solar system. These superlatives explain why astronomers remain determined to pursue further observations despite the technical difficulty of Alpha Centauri and the frustration of a vanishing signal. The scientific reward of confirmation would justify enormous effort. Crucially, the orbital models make testable predictions. If S1 is real, it should return to a favorable viewing position near aphelion in mid-2026. Statistical analysis of the allowed orbital families identifies August 2026 as the most likely window for redetection. If JWST observes Alpha Centauri A during that period and detects S1 near the predicted location, confirmation would be all but certain. A third detection, aligned with orbital predictions, would decisively demonstrate the presence of a gravitationally bound planet around our nearest Sun-like star. Researchers could then begin the detailed characterization that proximity uniquely allows. If, however, August 2026 passes without detection, despite favorable geometry, the mystery deepens. Either the planet follows an orbit outside current predictions, forcing a revision of the models, or the original August 2024 signal truly was an extraordinarily rare statistical illusion that evaded extensive testing. Either result points to a deeper reality. The vanishing planet exposes fundamental limits in exoplanet detection, even when using the most powerful telescope humanity has ever constructed. Orbital geometry creates brief windows of visibility, separated by long stretches of darkness. Worlds can exist, fully real and gravitationally bound, yet remain unseen. For nearby systems, these blind intervals are usually minor scheduling issues. Astronomers simply wait for favorable geometry and plan accordingly. Transit surveys work the same way, catching planets only during the fleeting moments when they pass across their stars from Earth's perspective. Alpha Centauri, however, refuses to play by those familiar rules. Its extreme proximity, something that should make observation trivial, introduces complications so severe that conventional techniques break down entirely. In this system, visibility windows are not a convenience. They are the dominant constraint, dictating what can be observed and when. The S1 episode is science functioning exactly as it should. An unconventional observation using novel methods revealed a provocative signal that survived rigorous statistical testing. Follow-up observations, conducted with the same care and methodology, produced unexpected null results that initially appeared contradictory. Subsequent theoretical work demonstrated that both outcomes can coexist within a single, physically consistent framework. A real planet on certain allowed orbits would be visible in August, invisible in February and April, and then reappear at predictable future dates. The non-detections neither prove nor disprove the planet's existence. They refine the range of possible orbits and sharpen predictions for future observations. This is how science advances, through cycles of detection, doubt, modeling, and verification. The story is unfinished. Its most important chapters will be written when JWST returns to Alpha Centauri during the next predicted visibility window. Regardless of the final verdict, the process itself has already taught us something profound. The James Webb Space Telescope has demonstrated that observations once considered impossible are now technically achievable. Alpha Centauri, an untouchable target for generations, has finally yielded measurable signals to human ingenuity and engineering. Whether those signals belong to a planet or to some unexpected phenomenon, the observational barrier has been broken. Our nearest sun-like star no longer hides completely behind blinding glare. JWST can now probe the region where temperate zone planets might exist. Future observations will gradually reveal whatever worlds inhabit this closest stellar neighborhood. The disappearing planet may return, or it may ultimately dissolve into a statistical mirage. Either outcome advances knowledge. Either result informs how we search for planets around other nearby stars. The techniques forged in the struggle with Alpha Centauri will be applied throughout the solar neighborhood. Science moves forward one observation at a time, transforming ambiguity into understanding through accumulated evidence. For now, S1 occupies the uneasy space between tentative detection and confirmed discovery. That uncertainty will not last forever. The universe does not keep its answers hidden indefinitely from persistent inquiry. For decades, astronomers have wondered whether planets orbit Alpha Centauri A. Within the next few years, that question will finally receive a definitive answer. The mystery of the disappearing planet will be resolved by the same empirical methods that created it. Now, imagine something no human has ever experienced. Picture yourself standing on the icy surface of a moon, orbiting a gas giant 4 light-years from Earth. Above you stretches an alien sky filled with sights so unfamiliar they steal your breath. Alpha Centauri. A burns overhead, bright, steady, and strangely comforting. This yellow-white sun looks remarkably like the star that warms Earth because in almost every meaningful way, it is the same kind of stellar engine, the same spectral class, nearly the same surface temperature. From a distance of roughly 2 astronomical units, its light feels gentler than Earth's noon sun, about a quarter as intense. Enough warmth to register on exposed skin, yet unmistakably dimmer. Then your eyes adjust and you notice something else. A second sun hangs in the sky. Alpha Centauri B glows a deep orange against the blackness, shining with a brightness comparable to Earth's full moon. It casts faint secondary shadows that slowly drift over decades as the 2 stars complete their 80-year orbital dance around a shared center of mass. 2 suns in one sky, a scene imagined by science fiction writers for generations. Now, evidence suggests such a view may actually exist. The world beneath your imagined feet defies simple description. S1 spans roughly 1 Jupiter radius, a massive Jovian planet with no solid surface on which anything could truly stand. What appears to be ground from afar dissolves into the upper layers of an atmosphere plunging thousands of kilometers downward into crushing pressure and searing heat. Bands of cloud wrap around the planet's equator in shades of tan, amber, and pale cream. In the frigid upper atmosphere, ammonia ice crystals condense into high-altitude hazes that scatter starlight into prolonged otherworldly twilights. Storm systems larger than Earth churn endlessly, driven by heat rising from deep within the planet and by uneven stellar heating between equator and poles. This alien giant completes an orbit around Alpha Centauri A every 2 to 3 Earth years, following an elongated path that subjects it to dramatically changing conditions. At closest approach, it receives roughly 40% more stellar radiation than at its farthest point. These variations drive atmospheric chemistry unlike anything we see in our own solar system, forcing scientists to rely on models informed by, but not limited to, observations of Jupiter and Saturn. The August 2024 measurements provide our clearest glimpse yet of this distant world. Every parameter carries uncertainty, but together they sketch a planet unlike any ever directly imaged. S1 emits a flux of roughly 3.5 millijanskis at a wavelength of 15.5 micrometers. That number represents how much mid-infrared energy reaches JWST from the planet's direction. Translating raw flux into physical reality requires complex modeling that accounts for atmospheric composition, viewing geometry, and internal heat. Brightness reveals temperature. According to the laws of physics established by Max Planck more than a century ago, working backward from the observed emission yields temperatures near 225 Kelvin, about -50 degrees Celsius. That makes S1 far warmer than Saturn, whose cloud tops average around 134 Kelvin. Neptune is colder still, plunging to roughly 55 Kelvin. Part of the difference comes from Alpha Centauri A itself. The star radiates about 50% more energy than our Sun, bathing nearby space in enhanced warmth. But stellar light alone cannot explain S1's temperature. Gas giants generate heat internally. Slow gravitational contraction converts potential energy into thermal energy that leaks outward over billions of years. Radioactive decay within the planet's interior adds to the warmth. S1 likely shares these same internal engines, supplementing the heat it receives from its star. Together, internal and external energy sources place S1 in a thermal regime between the frozen ice giants of our solar system and the blistering hot Jupiters found hugging other stars. Mass estimates derived from brightness and temperature point toward a Saturn-class planet rather than a Jupiter-class giant. Saturn weighs in at about 95 Earth masses, while Jupiter reaches 318. That distinction matters. These two categories of giant planets have fundamentally different internal structures. Radius estimates fall between 1 and roughly 1.1 Jupiter radii, meaning S1 is nearly Jupiter-sized while containing less than half the mass. This combination implies a bulk density lower than liquid water. Like Saturn, S1 would float, at least in principle, in a cosmic ocean. Such low density confirms a hydrogen-helium-dominated composition, exactly what giant planet formation models predict. These worlds gather enormous gaseous envelopes from the primordial disk during the earliest stages of stellar system evolution. If S1 truly exists, it is not merely another entry in an exoplanet catalog. It would represent an entirely new kind of neighbor, one orbiting the closest Sun-like star humanity will ever have the opportunity to study in detail. Unlike rocky planets assembled from heavier elements, gas giants form rapidly. They must capture vast quantities of hydrogen and helium before those lightweight gases disperse into interstellar space. At present, almost nothing is known about S1's atmospheric composition. The detection captured thermal emission from the planet's upper atmosphere, but provided no spectroscopic data capable of identifying specific molecules. That limitation leaves its chemistry entirely unconstrained. Future observations using JWST's spectroscopic modes could change that. Spectroscopy works by spreading incoming light into its constituent wavelengths and measuring how intensity varies across the spectrum. Molecules interact with light in precise, quantized ways, absorbing and emitting radiation at characteristic wavelengths. These molecular fingerprints allow scientists to identify atmospheric constituents even for worlds light years away. In our own solar system, Saturn's atmosphere is dominated by hydrogen and helium, with methane, ammonia, and trace hydrocarbons produced through photochemical reactions driven by sunlight. S1 likely hosts a similar chemical inventory, modified by Alpha Centauri A's slightly different stellar spectrum, and by the planet's warmer average temperature due to its closer orbit. Yet, chemistry alone does not explain why S1 is so compelling. Its position within Alpha Centauri A's habitable zone elevates the discovery from an interesting gas giant to something far more consequential. The habitable zone is the region around a star where rocky planets could, in principle, maintain liquid water on their surfaces. Too close, and water vaporizes. Too far, and it freezes solid. Between those extremes lies a narrow thermal band where liquid water, essential for terrestrial biology, can persist. For Alpha Centauri A, this temperate zone spans roughly from about 1.2 to 2.5 astronomical units, depending on assumptions about atmospheric greenhouse effects. Based on current orbital estimates, S1 spends much of its eccentric orbit within this region. If it were a rocky planet, its surface temperatures could plausibly support liquid water. But S1 is not rocky. It has no surface at all. Its immense atmospheric pressure would crush any Earth-like chemistry long before it could function. By every reasonable definition, the planet itself is uninhabitable. And yet, giant planets rarely exist in isolation. Every gas giant in our solar system hosts extensive moon systems composed of dozens or hundreds of satellites. These range from small, irregular captured bodies to large, world-sized moons with complex geology and atmospheres. Saturn alone is now known to possess more than 270 moons, a number that continues to grow as observational techniques improve. Titan, Saturn's largest moon, exceeds Mercury in diameter and maintains a dense nitrogen atmosphere thicker than Earth's. Liquid methane and ethane collect into lakes and seas across its frozen surface, while solar ultraviolet radiation drives complex organic chemistry in the atmosphere. Enceladus, far smaller, hides a global ocean of liquid water beneath its icy shell. Tidal heating generated by Saturn's gravity keeps this ocean warm, while geysers eject water vapor and organic molecules into space, clear evidence of subsurface activity. Many scientists consider Enceladus one of the most promising locations for life within our solar system. Jupiter's moon Europa tells a similar story. Beneath its frozen crust lies a vast ocean, possibly 100 kilometers deep, maintained by tidal heating from Jupiter's immense gravity. Hydrothermal vents on Europa's ocean floor could provide chemical energy similar to the environments where life thrives around deep-sea vents on Earth. Ganymede and Callisto likely harbor subsurface water layers as well, forming a family of ocean worlds with varying degrees of geological activity. If S1 follows the same formation patterns as Jupiter and Saturn, it should host a substantial satellite system of its own. Planetary formation models predict that giant planets naturally form circumplanetary disks from which moons condense. Some of those moons could be large enough to retain atmospheres and water, and here the implications become extraordinary. A moon orbiting S1 within Alpha Centauri A's habitable zone would receive gentle, sun-like radiation from the host star. Unlike the icy moons of our outer solar system, which rely entirely on internal heat to sustain subsurface oceans, such a moon could potentially support liquid water on its surface. Imagine a Titan-like world, but warm enough for water instead of methane. Rivers and lakes could form. Clouds could rise and fall in familiar hydrological cycles. Atmospheric chemistry might resemble environments where life arose on Earth. In that scenario, the detection of a gas giant becomes the discovery of potentially habitable real estate. We cannot directly observe moons around S1 with any existing instrument. From Earth's distance, the angular separation between a planet and its satellites would be far too small to resolve. But their existence follows naturally from everything we know about planetary system formation. The possibility that habitable moons orbit the nearest sun-like star carries staggering implications for astrobiology. If such moons exist, and if life can arise under those conditions, then living worlds may exist just 4 light-years away. That distance is not purely abstract. Concepts like breakthrough starshot envision laser-driven probes accelerated to a significant fraction of the speed of light. Such spacecraft could reach Alpha Centauri within a few decades, returning data within a human lifetime. The prospect of potentially habitable moons transforms speculative engineering into motivated mission planning. Yet the importance of S1 extends well beyond habitability. The Alpha Centauri observations pushed the James Webb Space Telescope to unprecedented limits of sensitivity. Consider the measurements of exozodiacal dust extracted from the same data that revealed the planet candidate. Zodiacal dust consists of microscopic particles generated by asteroid collisions and cometary activity. In our solar system, this dust scatters sunlight, creating the faint zodiacal glow visible near the horizon before dawn or after dusk. If Alpha Centauri A possessed a dense debris disk, like those seen around many younger stars, the scattered light could overwhelm planetary signals or produce misleading structures in coronagraphic images. In extreme cases, dense exozodiacal dust would make planet detection impossible regardless of instrument power. The JWST data place strong limits on such dust. Any zodiacal cloud around Alpha Centauri A must be only about 5 to 8 times brighter than our own solar system's dust environment. This represents the most sensitive exozodiacal dust measurement ever achieved for any star other than the Sun. Previous observations of other systems could constrain debris disks only to levels tens or hundreds of times brighter than our own. The Alpha Centauri observations pushed sensitivity an entire order of magnitude deeper. For the first time, astronomers can meaningfully compare another star's dust environment to the conditions in our own neighborhood. The relatively low dust levels suggest a mature, dynamically settled planetary system. Bright debris disks usually indicate recent major collisions or ongoing bombardment by comets. events that would pose severe risks to emerging biospheres. The apparent absence of such chaos around Alpha Centauri A is encouraging. Whatever planets or moons exist, they'll likely experience long-term stability favorable for biological evolution. Finally, the contrast achieved in the S1 detection deserves special attention. Isolating such a faint signal next to an overwhelmingly bright star pushes coronagraphic imaging to its absolute limits. Imagine trying to photograph a candle flame placed beside a lighthouse beam, while standing thousands of kilometers away. That is the level of contrast JWST confronted when searching for S1 next to Alpha Centauri A. The mere fact that any signal emerged at all stands as a remarkable achievement in optical engineering and data analysis. During the August observations, the apparent distance between the star and the candidate planet measured about 1.5 arcseconds, an extraordinarily small separation, yet just wide enough to fall within JWST's razor-thin zone of detectability. And within that narrow opening, something extraordinary revealed itself. At Alpha Centauri's distance, a separation of 1.5 arcseconds corresponds to roughly 2 astronomical units. While that angle may sound insignificant, it represents the smallest star-planet separation ever reached for any directly imaged exoplanet candidate. Previous direct imaging successes involved planets orbiting tens or even hundreds of arcseconds from their host stars. Those wide separations made detection far easier by keeping planets safely away from overwhelming stellar glare. S1 forced astronomers to do the opposite, pushing closer to the blinding heart of a sun-like star than any previous attempt had dared. The implications of S1's possible existence extend far beyond a single detection. For decades, binary star systems were viewed as hostile territory for planet formation. Gravitational interactions between stellar companions were thought to tear apart protoplanetary disks before planets could assemble. Alpha Centauri exemplifies this challenge. Its 2 main stars approach each other within about 11 astronomical units, creating strong gravitational disturbances throughout the region where planets might otherwise form. Simulations repeatedly predicted that such conditions would either suppress planet formation or prevent long-term orbital stability altogether. Only narrow safe zones appeared viable, close in orbits within roughly 1 to 2 astronomical units of each star, where a planet might remain gravitationally bound despite the companion's influence. Orbits farther out were expected to be destabilized. S1 appears to occupy exactly this fragile region. Its elongated orbit carries it between approximately 1 and 2 astronomical units from Alpha Centauri A, threading a narrow corridor between detectability limits and gravitational instability. It exists precisely where theory suggested a planet might barely endure. Yet the planet's inclination introduces an additional puzzle. Current models suggest S1 orbits at roughly 50 degrees relative to the Alpha Centauri AB orbital plane. Standard formation theory predicts that planets should form within disks aligned with stellar rotation and binary orbital planes. A strongly tilted orbit demands explanation. Several scenarios could account for this geometry. S1 may have formed on an initially aligned orbit that was later tilted through gravitational interactions with other planets that were subsequently ejected or remain undiscovered. Multi-planet systems often exchange angular momentum over time, reshaping inclinations across millions of years. Alternatively, the planet may have migrated through the protoplanetary disk early in the system's history, altering both its distance and tilt. More dramatic possibilities involve past dynamical upheavals, stellar flybys, long-term perturbations from the distant companion Proxima Centauri, or chaotic interactions during early binary evolution. Each scenario yields testable predictions. Discovering additional planets would support multi-body interaction models. Detecting subtle changes in S1's orbit could signal ongoing dynamical evolution. Improved measurements of the binary's motion might reveal traces of past instability. The broader consequences ripple across planetary science. Roughly half of all Sun-like stars in the Milky Way belong to binary or multiple star systems. If planets can form and survive around Alpha Centauri, despite its tight binary configuration, then countless other systems previously dismissed as barren may in fact host worlds of their own. With an estimated 200 billion stars in the galaxy and roughly half residing in binaries, around 100 billion binary systems await exploration. Even if only 10% host planets, That implies on the order of 10 billion worlds orbiting binary stars. A fraction of those could lie within habitable zones, dramatically increasing estimates of potentially life-supporting environments. Binary systems could double or even triple the number of habitable worlds inferred from single-star surveys alone. The Alpha Centauri observations also place strong limits on what is not present. The achieved sensitivity would have revealed any Jupiter-mass planets orbiting beyond about 2 astronomical units from Alpha Centauri A. Their absence suggests the inner system lacks additional giant planets in that region. This absence matters. Massive planets strongly influence the stability of smaller worlds. Systems crowded with giants often destabilize rocky planets through resonances and close encounters. A relatively uncluttered inner system leaves ample orbital space where Earth-sized planets could persist undisturbed within the habitable zone. Such worlds remain beyond current direct imaging capabilities, but other methods may eventually detect them. Radial velocity measurements can reveal stellar wobble caused by planetary gravity, though Earth-mass planets induce signals below 1 meter per second, challenging but within reach of next-generation spectrographs. Transit searches look for brief dips in starlight, though orbital alignment limits detection probability. Astrometry tracks minute stellar position shifts. Missions like Gaia are already refining these measurements and may one day uncover Earth-mass planets around nearby stars. Each detection technique probes a different slice of planetary parameter space. Direct imaging revealed S1 because it was large enough and far enough from its star to escape coronagraphic suppression. Smaller, closer worlds await discovery through complementary approaches. Beyond the science lies something deeper. Finding credible evidence of a planet around our nearest sun-like neighbor carries a psychological weight that goes far beyond numbers and statistics. For centuries, Alpha Centauri has held a singular place in human imagination, the closest destination beyond our solar system, the first star system we could realistically hope to reach. Long before astronomy could confirm whether planets existed there, storytellers and thinkers populated Alpha Centauri with alien worlds and distant civilizations simply because it was close, familiar, and tantalizingly reachable. Alpha Centauri became shorthand for humanity's longing to touch other stars. Now, for the first time, imagination is beginning to yield to observation. The nearest sun-like star may no longer be an empty beacon in the night. What was once only a hypothetical destination has begun to reveal itself through painstaking technical achievement. Whatever secrets Alpha Centauri ultimately holds, humanity has finally developed tools capable of pulling information out of the star's blinding glare. Whether S1 is eventually confirmed as a planet or fades into statistical uncertainty, the achievement itself is undeniable. Alpha Centauri's planetary environment is no longer beyond our reach. Barriers that shielded this system throughout all of human history have finally fallen to persistence, ingenuity, and engineering excellence. A Saturn-mass world may orbit within the habitable zone of our closest stellar neighbor. That world may host moons where liquid water exists beneath skies illuminated by 2 suns. Life may have arisen there through processes not unlike those that shaped Earth's biosphere. Or the system may prove sterile, devoid of the chemistry life requires. Either answer matters. Either outcome advances understanding. Both inform how we search for life elsewhere in the universe. The James Webb Space Telescope has forced open a door that remained sealed for all previous generations. What lies beyond that threshold will be revealed by future observations. The August 2026 observing window now looms like a verdict waiting to be delivered. Somewhere in the darkness between now and then, a Saturn mass object either is, or is not, tracing an eccentric orbit around the 3rd brightest star in Earth's night sky. The universe already knows the answer. We simply do not yet possess the data required to extract that truth from silence. The orbital models are clear. If S1 is real, and follows the family of stable trajectories consistent with current detections, it should return to a favorable geometry, where JWST's coronagraph regains sufficient sensitivity. Its elongated orbit will carry it back toward aphelion, emerging once more from the stellar glare that has concealed it since late 2024. Preparations are already underway. Telescope time proposals are being drafted. Data processing pipelines are being refined using hard-earned lessons from earlier campaigns. Across the astronomical community, anticipation builds as the predicted reappearance window approaches. If S1 reappears where the models predict, the case for confirmation becomes overwhelming. 3 independent detections spanning 7 years, the 2019 ground-based hint, the 2024 JWST detection, and a 2026 confirmation, would establish orbital motion consistent with a gravitationally bound planet around Alpha Centauri A. No statistical anomaly or background source could plausibly reproduce such a coherent, multi-instrument pattern. If, on the other hand, S1 fails to appear despite favorable geometry, the mystery deepens. Either orbital models will need revision to account for longer periods of invisibility, or the original detection will stand as one of the most improbable false positives ever recorded, an event that evaded every safeguard designed to prevent exactly that outcome. Both possibilities drive science forward. Confirmation unlocks unprecedented opportunities for exploration. Refutation sharpens methods and strengthens future searches. Progress emerges from both outcomes when interpreted with rigor. Yet the significance of S1 extends far beyond the fate of a single candidate. JWST has permanently changed what is observationally possible. Direct imaging of mature planets around Sun-like stars at extremely small angular separations is no longer theoretical. It has been demonstrated. The most powerful space telescope ever built has exceeded expectations its designers could not have fully envisioned decades ago. Consider what confirmation would enable. Atmospheric characterization would become achievable for the first time on a mature gas giant orbiting a Sun-like star. Repeated observations across different orbital phases would allow astronomers to track how S1's thermal emission changes as it moves between perihelion and aphelion. These variations encode information about atmospheric composition, vertical temperature profiles, cloud structures, and global circulation patterns. As S1 approaches Alpha Centauri A, increased stellar heating should drive chemical shifts and atmospheric dynamics. As it retreats, cooling should alter molecular abundances and spectral signatures. Monitoring these seasonal transitions offers insights impossible to obtain from one-time snapshots of distant exoplanets. No other known planetary system offers such an opportunity. Most directly imaged exoplanets orbit young stars, where residual formation heat dominates their emission. Their atmospheres reflect primordial conditions rather than the evolved states of billion-year-old worlds. S1 would provide the first true analog for studying how gas giant atmospheres behave after long-term evolution, making it directly comparable to Jupiter and Saturn. Spectroscopic observations could reveal methane, ammonia, water vapor, and complex hydrocarbons through their distinctive mid-infrared signatures. Comparing these measurements with the solar system giants would illuminate how stellar radiation, orbital distance, and planetary mass shape atmospheric chemistry. Orbital dynamics would also come into sharper focus. Each new observation further constrains allowed orbital solutions, eliminating configurations inconsistent with measured positions. Over longer time baselines, subtle gravitational perturbations from unseen planets could be detected as deviations from simple two-body motion. Such perturbations would betray the presence of additional worlds too small or too close to detect directly. S1's unusual inclination and eccentricity provide a natural laboratory for testing theories of planetary survival in binary systems. Gravitational torques from Alpha Centauri B should slowly alter orbital parameters over time. Measuring these changes would directly test long-term dynamical stability models. Looking further ahead, moon searches become conceivable. JWST cannot resolve satellites around S1, but the next generation of extremely large ground-based telescopes may. A sufficiently large moon orbiting far enough from the planet could produce a separable signal. Several revolutionary facilities are nearing completion. The extremely large telescope in Chile's Atacama Desert will deploy a 39-meter primary mirror, 4 times larger than any existing optical telescope. Its advanced coronagraphs will push contrast and angular resolution beyond current space-based limits. The 30-meter telescope, planned for Mauna Kea and the Giant Magellan Telescope, with its 7-mirror 25-meter equivalent aperture, will deliver comparable leaps in capability. Within a decade, these observatories will scrutinize Alpha Centauri with precision far exceeding today's standards. If S1 is real, its orbit will be traced with sub-millisecond accuracy. Atmospheric properties, orbital evolution, and perhaps even large moons may eventually come into view. What began as a fleeting point of light beside a familiar star may ultimately redefine how humanity understands its closest stellar neighbor, and its place in a universe that is far richer and far nearer than we once believed. If additional planets inhabit the Alpha Centauri system, future instruments with larger apertures and more advanced coronagraphs will detect them where today's telescopes see only darkness. The implications extend beyond astronomy into the realm of interstellar exploration. Mission planning gains a tangible destination, transforming speculative engineering into focused, goal-driven development. Projects like Breakthrough Starshot have long proposed sending gram-scale spacecraft toward Alpha Centauri at relativistic speeds using powerful ground-based laser arrays. These concepts envision accelerating tiny probes to roughly 20% of the speed of light, allowing them to reach the system in just over 20 years. For decades, such ideas felt almost quixotic. Why invest enormous resources to reach a star system that might contain nothing of interest? That uncertainty dampened enthusiasm. The presence of planets changes the equation entirely. Mission architects can now design objectives around known targets. Trajectories can be optimized for predicted orbital positions. Instruments can be tailored to measure specific planetary characteristics, rather than scanning blindly. The prospect of habitable moons, orbiting S1, elevates motivation even further. A Titan-sized satellite residing in the habitable zone could be examined up close for biosignatures beyond the reach of Earth-based telescopes. Atmospheric chemistry might reveal oxygen, methane, or other gases indicative of biological processes. High-resolution imaging could identify liquid water features, or even surface patterns suggestive of vegetation. The scientific value of such discoveries would justify almost any conceivable mission cost. Even in the absence of life, close-range observations would revolutionize comparative planetology. Humanity currently understands gas giants through just 4 examples in our own solar system, supplemented by distant exoplanets observed under severe limitations. S1 would offer a 5th detailed case, formed in a different stellar environment, under different initial conditions. Comparing its atmospheric dynamics, magnetic field, ring system, and moons to Jupiter and Saturn would reveal how giant planets evolve across diverse cosmic settings. Yet the broader impact of the S1 detection does not depend on confirmation alone. It proves that mature planetary systems can be studied through direct imaging when instruments are pushed beyond their nominal limits. That success encourages similar attempts around other nearby stars previously considered impractical targets. Tau Ceti lies about 12 light-years away, 3 times farther than Alpha Centauri, but still close enough to attempt direct imaging with refined techniques. This sun-like star already hosts several planetary candidates detected through radial velocity measurements. Some may be massive enough and sufficiently separated to emerge from coronagraphic suppression using methods pioneered at Alpha Centauri. Epsilon Eridani, at just over 10 light-years distance, offers another compelling case. Though farther than Alpha Centauri, it remains nearby in cosmic terms. Its youth, only a few hundred million years old, and its prominent debris disk suggest active planetary evolution. Any planets there may still glow brightly from formation heat, making them easier targets than the cold, mature worlds suspected around Alpha Centauri A. The binary system 70 Ophiuchi presents yet another intriguing possibility. Located roughly 16 light-years away, its 2 orange dwarf stars orbit each other with a period of about 88 years, creating a gravitational environment reminiscent of Alpha Centauri. If planets can survive in one such system, perhaps they exist in the other as well. Sirius offers a different challenge. At just 8.6 light-years, it is the brightest star in Earth's night sky. Its intense glare and white dwarf companion complicate observation, but also raise fascinating questions. Any planet that survived the violent transformation of Sirius B into a white dwarf would occupy an extraordinary orbit, worthy of detailed study. Each nearby system presents unique opportunities, if direct imaging techniques can be adapted to overcome their individual challenges. The Alpha Centauri campaign has demonstrated both that such observations are feasible and how to achieve them. Techniques like blind offset acquisition, reference star subtraction, and advanced data reduction pipelines can be applied to many other targets with appropriate refinements. The implications extend far beyond individual planetary systems to the most fundamental questions humanity has ever asked. Since we first realized that stars are distant suns, we have wondered whether life exists elsewhere. The Drake equation, proposed by Frank Drake in 1961, attempted to formalize that curiosity by estimating how many technologically capable civilizations might exist in our galaxy. It multiplied factors such as star formation rates, planetary occurrence, and the probability of life emerging and evolving intelligence. Before the exoplanet era, astronomers fiercely debated whether planets were rare or common. Some models suggested that planet formation was inefficient and fragile. Others argued it was nearly inevitable. The discovery of thousands of exoplanets over the past 3 decades settled that debate decisively. Planets are everywhere. Nearly every star hosts at least one. The planetary term in the Drake equation is close to 1. What remains unknown is life. Despite this abundance of worlds, we have exactly one confirmed example of life emerging: Earth. From a statistical perspective, that single data point tells us almost nothing. Life may arise wherever conditions allow, or it may require such extraordinary coincidences that Earth is an anomaly in an otherwise lifeless cosmos. Potentially habitable environments around Alpha Centauri change how we confront that uncertainty. If moons orbiting S1 possess liquid water, the closest stellar system we can meaningfully study becomes a laboratory for questions no distant target can resolve. A probe traveling at 20% of light speed could reach Alpha Centauri in about 21 years. Including communication delays, data could return to Earth within roughly 25 years, well within a human lifetime. No other sun-like star offers such accessibility. The next nearest solar analogues lie 2 to 3 times farther away, stretching mission timelines to 50 years or more. Red dwarfs like Barnard's star and Wolf 300 Syn are closer in distance, but fundamentally different from the Sun. Tau Ceti and Epsilon Eridani are promising, yet far less reachable. Alpha Centauri stands alone. It is humanity's only realistic interstellar destination within the next century. That reality magnifies the importance of every discovery made there. Even an unconfirmed candidate like S1 reshapes how engineers and scientists think about what future missions might achieve. Propulsion systems can be designed for specific distance and velocity requirements. Communication architectures can account for precise signal delays. Scientific payloads can prioritize instruments optimized for known planetary targets. Concrete objectives accelerate innovation in ways abstract possibilities never can. And we do not need to wait for interstellar probes to deepen our understanding. A new generation of ground-based observatories will transform exoplanet science within the next decade. Chief among them is the Extremely Large Telescope. With a 39-meter primary mirror, it will collect more light than all existing large telescopes combined. Advanced adaptive optics will correct atmospheric turbulence in real time, achieving angular resolution rivaling, and in some cases exceeding, space-based observatories. First light is expected before 2030. The ELT's coronagraphs will push contrast ratios and inner working angles far beyond current limits. Worlds now buried in stellar glare will become detectable. Atmospheric spectra currently lost in noise will reveal their chemical fingerprints. The Alpha Centauri system, so difficult for JWST, will become a routine target for detailed study. What began as a single, fragile signal has already redefined the limits of what humanity believed possible. Whether S1 ultimately proves to be a genuine planet or an elaborate illusion produced by extreme observational conditions, the trajectory forward is unmistakable. A threshold has been crossed. Our nearest sun-like neighbor is no longer beyond reach, and, in a very real sense, the universe has become smaller. The upcoming generation of ground-based observatories will amplify this shift dramatically. Facilities such as the 30-meter telescope and the Giant Magellan Telescope offer complementary capabilities from distinct geographic locations. Their global distribution enables near-continuous monitoring of high-priority targets and provides resilience against weather disruptions or technical downtime. Together, these observatories represent a leap in observational power unlike anything astronomy has previously possessed. Within the next 15 years, these instruments will examine Alpha Centauri with sensitivities far exceeding what JWST can currently achieve. If S1 exists, ground-based telescopes will refine its orbit with extraordinary precision. If additional planets occupy smaller separations or possess lower masses, these facilities will detect them. If hypothetical moons harbor atmospheric biosignatures, advanced spectroscopy may uncover them. At the same time, the James Webb Space Telescope itself continues to evolve. Operational teams steadily improve performance as experience accumulates. The Alpha Centauri campaign revealed valuable lessons about observing extreme brightness targets, lessons now shaping more refined strategies for future observations. New data reduction techniques extract additional sensitivity from existing hardware by better isolating and suppressing systematic noise. What appeared to be JWST's performance ceiling during the August 2024 observations may not represent its ultimate capability. Continued refinement could enable detection of even fainter signals at smaller angular separations. Beyond JWST, future space missions purpose-built for exoplanet imaging are progressing through development pipelines. The Habitable Worlds Observatory, recommended by the most recent Astronomy and Astrophysics Decadal Survey, aims to directly image Earth-like planets around nearby stars for the first time. This mission concept incorporates hard-won lessons from JWST, the Roman Space Telescope, and ground-based coronagraph experiments. The Alpha Centauri observations provide invaluable real-world data for these designs, defining required contrast ratios, angular separations, and dominant noise sources. Success at Alpha Centauri validates approaches that might otherwise appear overly optimistic on paper. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will further advance this progression. Though its primary mission focuses on wide-field surveys, Roman includes a coronagraph technology demonstration capable of testing starlight suppression beyond any currently operational system. Each incremental advance brings humanity closer to addressing one of the most profound questions ever asked. Are we alone? The search for life beyond Earth drives a vast portion of modern astronomy, planetary science, and astrobiology. Every exoplanet detection adds a data point toward resolving this existential mystery. Discovering planets around Alpha Centauri advances this endeavor more directly than almost any other conceivable finding. The same proximity that complicates observation also magnifies its importance. Whatever we learn about this system applies immediately to understanding our own cosmic neighborhood and the prospects for life within eventual reach. Yet the implications of S1 extend beyond science into philosophy. For nearly all of human history, the stars were distant, untouchable lights embedded in myth and symbolism. Ancient civilizations constructed cosmologies around patterns that seemed eternal and unreachable. The heavens appeared fundamentally separate from the fragile, transient human world below. The scientific revolution overturned that division. Roughly 4 centuries ago, astronomy revealed stars as distant suns, nuclear engines governed by the same physical laws operating on Earth. Quantum mechanics explains both laboratory spectra and stellar atmospheres billions of kilometers away. The universe became unified under natural law. The exoplanet revolution of the past 3 decades completed that unification. Planetary systems are not rare exceptions, they are the norm. The same processes that formed Earth operate throughout the galaxy, producing rocky planets, gas giants, ice worlds, and configurations never imagined before. Statistical inference suggests billions of potentially habitable worlds exist in the Milky Way alone. Yet, for all that knowledge, it remained abstract. We knew planets existed in vast numbers without knowing much about specific nearby systems. The third brightest star in Earth's sky, visible to the naked eye for all of recorded history, remained a mystery. Alpha Centauri guarded its planetary secrets behind overwhelming glare. That has now changed. For the first time, a specific planetary candidate has been detected around an individual nearby sun-like star. Abstract population statistics collapse into concrete reality. That familiar point of light shining from the southern sky appears to host its own planetary system, including at least one massive world orbiting within the habitable zone. This shift fundamentally alters humanity's relationship with the cosmos. We are no longer passive observers cataloging distant anonymous systems. We are participants in a local stellar neighborhood. The 37 light-years separating Earth from Alpha Centauri still represent an immense gulf, But that gulf has transformed from an unreachable void into a challenge of engineering rather than a barrier of principle. Physics does not forbid crossing it. Only technology stands in the way. For generations, science fiction envisioned Alpha Centauri as humanity's first interstellar destination. Writers placed alien civilizations and habitable worlds there without evidence, guided solely by proximity and imagination. Now, imagination inches toward observation. We cannot yet confirm life or habitable moons, but we can say with evidence that at least one planetary candidate orbits our nearest sun-like stellar neighbor. The universe feels closer now, not because the vast distances between stars have diminished, but because our understanding has expanded to meet them. What was once only imagined has begun to reveal its true nature through the slow, deliberate accumulation of photons captured by instruments stationed 1,000,000 miles from Earth. The universe does not surrender its secrets quickly. It yields them only to civilizations capable of building the right tools and possessing the patience to wait for answers measured in years, decades, or generations. Humanity has wondered whether planets orbit Alpha Centauri ever since we first realized that stars might host worlds, just as our sun hosts Earth. That question persisted across centuries of curiosity and technological progress, surviving eras when the answer remained permanently out of reach. Each generation refined the tools, sharpened the methods, and pushed a little closer to truth. The James Webb Space Telescope represents the culmination of that long effort. It is the result of decades of work by thousands of scientists and engineers who designed, built, tested, launched, and now operate the most powerful astronomical observatory ever created. Their collective achievement has delivered the first meaningful response to a question that haunted astronomers who came before them, those who could only speculate because the technology to know did not yet exist. That answer, for now, remains provisional. Confirmation awaits future observations during predicted visibility windows. The 2026 campaign will either verify S1's existence or deepen the mystery surrounding its apparent disappearance. Either outcome moves understanding forward. Either result generates new questions that demand further investigation. Science advances not by certainty alone, but by narrowing ignorance one observation at a time. Yet regardless of what 2026 ultimately reveals, one conclusion is already secure. Alpha Centauri's planetary system is no longer beyond our reach. For the first time in human history, the observational barriers that shielded this nearby stellar system have yielded to ingenuity, persistence, and engineering excellence. Whatever worlds populate our closest stellar neighborhood, we now possess instruments capable of detecting them. The fireflies beside the cosmic searchlight, once lost in glare, have finally begun to show themselves to observers willing to push technology beyond its nominal limits. The nearest sun-like star to Earth no longer enjoys perfect privacy. Its planetary companions, whether one or many, whether ultimately confirmed or still debated, have begun to emerge from the brilliance that concealed them since the first humans looked up and wondered what lay beyond the stars. A gas giant world may orbit within the habitable zone of Alpha Centauri A. That world may host moons where liquid water gathers beneath alien skies, illuminated by two suns tracing their slow, gravitational dance. Life may have arisen there through processes echoing those that unfolded on Earth billions of years ago. Or the system may prove barren, its worlds lifeless, shaped only by physics and chemistry without biology. Either answer matters. Either outcome deepens humanity's understanding of its place in a universe that increasingly reveals itself as filled with worlds beyond counting. The James Webb Space Telescope has forced open a door that remained sealed throughout all previous human existence. What lies beyond that threshold will be revealed through continued observation, patience, and refinement, until mystery hardens into knowledge. The August 2026 observation window approaches. The universe already knows whether S1 will reappear at the predicted location or remain hidden despite favorable geometry. We simply wait for the light that will carry that answer across 4.37 light-years of emptiness to detectors poised in the darkness beyond Earth's atmosphere. Whatever that light reveals, the search will not end. Other nearby stars await similar scrutiny. Other planetary systems will surrender their secrets to telescopes even more powerful than JWST. The cosmic neighborhood that once seemed permanently unknowable has begun transforming into territory we can methodically explore and, eventually, understand. The impossible observation has already been achieved. The nearest Sun-like star has revealed at least one planetary candidate to instruments pushed beyond their intended limits by scientists unwilling to accept that some questions were too difficult to ask. That achievement cannot be undone, regardless of what future observations conclude about S1 itself. Humanity has looked into Alpha Centauri and discovered that planets almost certainly exist there. The precise number, masses, and orbital architectures remain to be determined through continued investigation. But the foundational question that motivated generations of astronomers has finally received its answer. Our nearest stellar neighbor hosts worlds of its own. With every planetary detection around nearby stars, the sense of cosmic isolation grows a little weaker. Whatever S1 ultimately proves to be, its detection marks a turning point, a moment future generations will recognize as the instant Alpha Centauri finally yielded to human curiosity. The stars are not merely lights in the sky, they are suns with planets of their own, and the closest ones are finally revealing themselves to observers patient and bold enough to look.